Hello friends. So today we are going to solve two questions from the rotational motion, and in the first question it is said that a uniform pencil model as thin rod of mass m and length L lies at rest on a frictionless horizontal table. A constant force F, always perpendicular to the rod, is applied for time t. So based on this we are having two things which are asked on it. The force is applied at the rod's midpoint. Find the final center of mass speed, the distance of rod center of mass, and the contact point travels during the push. Verify that the work done equals to the final kinetic energy. And in the part B, the same force F is instead applied at one end of the rod, still perpendicular. Assume t is small enough that the rod does not complete large rotations. Okay. Find the center of mass speed, the final angular speed about the center of mass, the distance your hand, the contact point, moves during the push, and verify that the work done equals to the final total kinetic energy, which will be a combination of translational as well as the rotational. Okay. So in this case we have two parts, and in the part A we are pushing the rod or pencil through the center of mass, and in the part B we are pushing the rod at one of its end. So this is the one of the major difference between this. Okay. And so let us start with our part A. And for part A, the rod is pushed through the center of mass. Okay. So we have a rod and length is given as L and mass is our m. So we have a length L and its mass is given as m. So let us suppose this is our center of mass and the force F is being applied at this center of mass. So in this case, since the force is applied at the center of mass, so there will be no torque about the center of mass. So this is one of the key difference between the part A as well as part B. You can say that force acts at the center of mass, therefore we can write no torque about center of mass. No torque about the center of mass. And so it means the force is going to result in the rod's motion that will be constituting only the translate without rotation. Therefore we can say the force causes the rod to translate without rotation. So let us find out the impulse with respect to the rod. Therefore, we can say that the impulse delivered to the rod, impulse delivered to the rod, that is our J, will be equal to F multiplied by time t, because the force is applied for the time t. And therefore, we can find out the change in the linear momentum of our center of mass. You can say that this changes the linear momentum of the center of mass. And in terms of equation, we can write this as our mass into velocity of our center of mass will be equal to impulse, that is our F times t. Therefore, from here we can say that the velocity of our center of mass will be equal to Ft divided by m. Okay, this is the velocity of our center of mass. Now, we can easily find out the distance traveled by the center of mass. Let's say distance traveled by center of mass, and we have a force S F applied. Therefore, we can say that our acceleration of the center of mass, if that is our A, then this A will be equal to force divided by mass m. And rod initially was at rest. Therefore, we can use our kinematics equation and get the distance formula. So we can say the rod starts from rest therefore, we can say so displacement in time t, if that is written as our d, then this t will be equal to our half at square. And we substitute value of a, which we just found out. So this comes as our half and f t square upon m. So this is the displacement, and from this displacement we can easily find out the work done. So we can say work done by the force and that force is of F. So work done is suppose of W, then this W will be equal to force multiplied by the displacement, and we substitute value of our displacement, that is our force F times Ft square upon 2m. So this gives us that the work done will be equal to F square T square upon twice m. So this is our amount of work done. Now we are supposed to find out what will be the kinetic energy and whether this kinetic energy is equal to work done. This is one of the questions that has been asked in part A. Therefore, we can say that the final kinetic energy and as the motion is pure translational, there is no rotational motion because we are applying the force at the center of mass. So it is having the kinetic energy that will be pure our translational. which will be coming as our half m velocity of our center of mass square, and VCM we already know. Therefore we can say that our kinetic energy final, which is our kinetic energy translational, will be equal to substitute value of VCM. So this comes as our half, and our VCM is our Ft upon m. So this comes as Ft upon m and whole square, and m square and square goes away, so this comes as our F square T square upon twice m. Therefore we can write that our kinetic energy final is equal to our work done. Okay, that was our one of our part. Okay. And now we come to our part B, and in our part B same question is there, but now the force is being applied at the, you can say, one of the ends. We have part B. So in this case, the force is being applied to one of its end, but the time for the force is being applied is our t, that is not changed. And in the question it is also mentioned that the rotational is negligible, so simply we can ignore it. Therefore we can say that our force F is applied perpendicular to the rod for time t. So this time t is same for our first part as well as this part also, and it is mentioned in the question that our t is small, such that rotation during the force is negligible. And obviously this table is frictionless, so the rod is free to rotate as well as the translate. Okay. And once again we start with the linear motion of center of mass. Linear motion of center of mass, and we can find out our acceleration of our center of mass will be equal to our force divided by m. And okay, let me put it separately. So we have linear motion of center of mass, and we start with acceleration of center of mass, that is our ACM, will be equal to force oblique mass, and we can also find out the velocity of center of mass after time t, because force is being applied for time t. So you can say velocity of center of mass after time t, and that is suppose over VCM, which will be equal to our force multiplied by time and divided by mass m. Okay, this is almost similar to our first part. And next we can find out our rotational motion about the center of mass. So we have our rotational motion about the center of mass, and for that we will be requiring the moment of inertia. Therefore we can say the moment of inertia of rod about center of mass, let us suppose that is given as I, then this I will be equal to 1/12 ml square. And from here we can also find out our torque, because force F is being applied at a distance L/2 from the center of mass. Therefore we can say that our torque about center of mass is, suppose our tau is equal to force multiplied by the lever arm, that is our L/2. And now we can easily calculate our angular impulse. Angular impulse delivered during time t. During time t, and we can write that equation will be our tau multiplied by t, and which will be equal to our I times omega, and from here we can say that our omega is equal to tau t upon our I, and we already know value of our tau as well as I, so we can write this our I is our moment of inertia 1/12 ml square, and tau is our F L/2 and multiplied by our t, and this will be giving us this L square goes away and 12 goes by over 6. Therefore we get this will be equal to 6 ft and divided by ml. This is our angular impulse delivered during this time t. Now we come to our displacement of the contact point. Okay, and the contact point is nothing but, because we are applying the force with the help of the hand. Okay, so this is our contact point. Contact point, and we have to find out its displacement. So we can say displacement of the contact point and we know that the contact point is going to have two velocities. One will be our translational, other one will be our rotational. Okay, and so we can write that our contact point here, contact point is where the force F is being applied. So contact point velocity is the sum of first will be the translational velocity, that's the velocity of our center of mass. So you can say translational velocity of center of mass, and that is our VCM, which will be equal to our Ft divided by m. And second comes our rotational velocity, rotational velocity, and rotational velocity will be equal to, suppose our v rot will be equal to our omega multiplied by our L by 2, and omega we just found out is our 6 ft upon ml, so this comes as 6 ft upon ml times L by 2. Here this length and 6 goes by 3, therefore it will be coming as our 3 ft divided by m. But in this case we have to remember that the question specifically states that the rotation is negligible, and for that, in ideal case, if the rotation is not negligible, so we can, because our this velocity of the center of mass will be perpendicular rod, and if the rotation is not negligible, then this is going to, here force F is being applied, so it will try to rotate by a certain angle, and accordingly this V rotational will be our tangential to this, the, you can say, imaginary circle. But here this rotational is angle is very small, therefore this V rotation we can assume, or we can say draw a conclusion, will be perpendicular to the rod, and this is our VCM. So velocity of a center of mass as well as the velocity of a rotation is our in same direction. Okay, it is much more easier to understand that. I think we already deal with this concept numerous times during study of rotational motion, and if we consider a point that is somewhere on the near the edge of the sphere, so here it is going to have two types of velocities. One velocity will be equal to velocity of a center of mass, and this point is going to rotate in a circle. Okay. So other velocity will be tangential to is, which we call as our V rotational. Okay. Same concept is applicable here also, but on a straight rod. So in this case, so we are going to have that our velocity of center of mass as well as V rotational are in same direction. So we can say that our V center of mass and V rotational are in same direction. Are in same direction. Okay, that is perpendicular to the rod. Perpendicular to the rod. Therefore, we can write that our total velocity, or we can say velocity of the rod, will be equal to velocity of our center of mass plus velocity of our due to rotation, and this will be, if you substitute the values, we are going to get this as our Ft upon m plus 3 Ft upon m, which gives us that the velocity of the rod is equal to 4 Ft upon m. And because this force is applied for a fraction of a second, that is, time is very small, therefore we can, for that time we can assume that it is having a constant acceleration. We can say that for short period of time t, we can write this as our acceleration of the rod will be equal to, we have our velocity of the rod and divided by time t. So this comes as our 4 ft divided by t and multiply by m. So this t and t cancels out. So we get this as a 4f divided by m. And now we can easily calculate our displacement. So we can say the displacement of the contact point let us call this a d, and that will be equal to over half acceleration of the rod and t square, because initially the rod was at rest. And therefore we substitute value of our this acceleration of rod, so we get a displacement is equal to over half, and we have this is 4fm and multiply by t square, and this 4 goes by 2, so we get this as our 2f t square upon m. So this is our displacement, and now we can easily find out our work done. So we can say our work done, if that is our w, will be equal to force multiplied by our displacement, and this will be giving us 2f square t square upon m. And we can find out the kinetic energy, because that is being asked what will the kinetic energy, whether it will be equal to our work done or not. Therefore we can say that our final kinetic energy, and let us call this as Ke final, will be our summation of, because it is having both motions, translational as well as rotational. So this will be kinetic energy translational plus kinetic energy rotational, and we can simply, so our translational will be equal to over half m velocity center of mass square plus, and this comes as our half I omega square, and we can take, or we can just substitute the values, later on we can deal it. This is our half m, velocity we know is our ft upon m whole square, plus this comes as our half, and the moment of inertia we know is a 1 upon 12 ml square times omega, we calculated it as our 6 ft ml. So this comes as our 6 ft ml and whole square. And now this is only simple calculation. So in the first part, this m square is going to cancel with m, so we get this as our f square t square upon 2m, and in the second part we are getting 36, and this will be 3, so this will be 3 by 2, and we are having this square will be cancelled with our m, so we get in the numerator will be our f square t square, and we have our, this is L not T, so L square and M square, so this will be coming as our M. So their summation will be equal to, and this will be coming as 3 plus 1 4, 4 goes by 2, So we are left with 2f square t square upon m. Okay. So therefore we can see that our total kinetic energy is equal to our work done. Okay. That was our this. So finally we can say that our work done is equal to our kinetic energy final. So this relationship is true for both part A as well as our part B. We come to the next question. And this question states that we are having a super ball is given an initial velocity and bounces repeatedly between two fixed points on the ground or between two fixed surfaces. The ball behaves like a uniform rigid sphere and experiences impact with the ground characterized by a coefficient of restitution E. The ball rolls without slipping at the point of contact to the ground. So based on this, we are having two questions. Relationship between the angular and horizontal velocity. Find the relationship between the ball's angular velocity omega and its horizontal velocity Vx that ensures the ball follows a repeating single leg trajectory, that it always bounces between same two fixed points on the ground. And part B, the angle of rebound. If the peak height of the ball's parabolic trajectory between the bounces is h, determine the angle theta that the ball's velocity vector makes with the horizontal immediately after each bounce. So this question little bit looks complicated, but it's quite easy to solve because it is the only term that is little bit confusing is our single leg trajectory, and its meaning is already explained in the question. It always bounces between two fixed points. Okay. So let's start with our part 1. And part 1 is nothing but our single leg trajectory. It means it is going to bounce between two fixed points. And let us call these two fixed points at A and B. Okay. So we can say that two fixed points are A and B at a distance capital L apart. And this is, you can see this this motion is repeated between A and B continuously. Okay. So the figure will be quite simple. So this is our point B, this is point A, and the distance between the two is our L, and the ball is repeatedly bouncing between these two. So it means the horizontal velocity will be the negative of our incoming velocity. Okay. Therefore, we can write that for the motion to repeat identically after each bounce, following conditions must hold. following conditions must hold. Okay. So first is our, so the first condition we can say that our horizontal velocity of the center of mass after the bounce must be equal to the before the bounce, but with the negative sign because of our direction. Okay. We can say that our horizontal velocity of center of mass after bounce equals negative that before bounce, or in terms of equation we can write this as our Vx prime should be equal to negative of Vx, and this was our velocity of a center of mass. And the second condition is for our angular velocity. Okay. So we can say that our angular velocity after bounce equals our negative that before bounce. So which means that our omega prime should be equal to minus of omega. So if these two conditions are satisfied, then it is going to bounce continuously, repeatedly between point A and point B. Okay. And here we have to remember that Vx is our horizontal velocity just before our impact, and omega is angular velocity just before impact, and the prime version is after the impact. And we know the standard condition for our no slip motion. So we can say for no slipping condition, we can write for no slipping condition, we can write that our for no slipping condition at the bottom point of the sphere. Okay. And which is basically distance r below the center of mass. Distance r below center of mass. Okay. So this ball is having a radius r, and we can write that our Vx minus r omega should be equal to negative of our their prime version, Vx prime and our r omega prime. And as the ball is striking the ground, the impulse will be purely vertical. So we can say that because the impulse from ground is purely vertical, which means that our horizontal impulse is 0. Horizontal impulse is 0. So it means the horizontal velocity of center of mass is unchanged. Therefore, we can say that the horizontal velocity of center of mass is unchanged. Therefore, from here we can write that our Vx prime will be equal to our Vx. And let us call this previous equation our 1 and this equation as our 2. So therefore, from equation 1 and 2, from equation 1 and 2, we can write this our, if we substitute our Vx prime as our Vx, we can write this our Vx minus r omega will be equal to minus of our Vx and minus of our r omega prime. And we can just sort it out and we can write this as our r omega prime will be equal to twice Vx minus r omega. And from here we can say that our omega prime is equal to twice Vx upon r minus our omega. And for repetition condition, we have already said that Vx prime should be equal to our Vx and omega prime should be equal to our minus of omega. Okay, so these are the two repetition condition. And it means, so let me put it here. So we said that for repetition, we should be having that our Vx prime should be equal to minus of Vx and omega prime is equal to minus of omega. These two conditions should be satisfied for the repetition. Okay. Which is, from here we can say that omega prime is a little bit complicated equation, at least is not negative of omega, and similarly our Vx prime is also equal to our Vx. So these two conditions are not satisfied by the given calculation which we did it. So it means, so this means that our purely vertical impulse cannot reverse the horizontal velocity of center of mass. So this was our, sorry, I forgot to mention here one important thing, that this is conflicting with equation 2. Okay. Let me put it here. So this is conflicting with equation 2. Okay, because equation 2 gives us that a Vx prime is equal to Vx. It means after and before the bounce, the velocities are equal. Okay. And now we come to our no slip, or we can say the pure rolling condition at impact. we can say our no slip or pure rolling, and for that we can write that the ball spins so that the contact point velocity is 0 just before the impact. Okay. So we can say that for repeating bounce between two points, the ball spins so that the contact point velocity contact point velocity is 0 just before impact. Just before impact. So if we substitute this condition, we can write that our Vx minus r omega is equal to 0, or we can say that our omega is equal to velocity in x direction, that is horizontal, divided by our r. And next we can find out the horizontal distance between the bounce points. Horizontal distance between bounce points. And if we say that velocity in y direction at a height so the vertical velocity at the takeoff point from height h let us call this as v of y naught will be equal to our 2gh and its square root. And we can find out the time of flight from our ground to the peak as well as back. So we can say the time of flight from ground to peak and back. Let us call this as t. So obviously that will be our twice of our the vertical velocity divided by g. So this comes as twice vy naught and divided by g. We substitute our vy naught, so this comes as 2 by g square root of 2gh. And we can simplify it a little bit. We can write this as our 2 square root of, this comes as our 2h upon g. So this is our time of flight, and during this time of flight we can find out our the horizontal distance. So we can say that horizontal distance traveled in time t, and let us call this a distance as L. So we get L is equal to Vx multiplied by time of flight, that is our t. So we get this as twice Vx square root of 2h upon g. And so the ball is going to repeat this flight back and forth, so maintaining same our v of x as well as our omega. So we can say that the ball repeats this flight back and forth, thus maintaining our v of x and our omega, and omega is nothing but our Vx upon r. And now we can easily find out our angle of rebound, which were asked in the part B. So we can say that our angle of rebound, and if that is our theta, then the theta is the angle the velocity vector of the center of mass makes with the horizontal immediately after the bounce. So we can say our theta the angle velocity vector of center of mass makes with the horizontal. And makes with the horizontal immediately after the bounce. Immediately after the bounce. And we already know the condition for our horizontal velocity. So we can say that our horizontal velocity after bounce that is our Vx prime is equal to our Vx, and our vertical velocity we just calculated. Vertical velocity after bounce and we are given the coefficient of restitution as our E. So this we get a Vy prime will be equal to E times our Vy naught. So we substitute our Vy naught, so we get this our Vy prime is equal to E times square root of 2gh. Okay, and so finally we can say that our tangent of theta will be equal to our Vy prime upon Vx. So therefore we get this as our 2gh upon Vx, and if required we can substitute value of Vx in terms of our L, because we know that our Vx is equal to L upon twice square root of 2h upon g. Therefore we can say that our tan of theta will be equal to E square root of 2gh, and this comes as our L divided by twice square root of 2h upon g. So we get this will be equal to our GHL, so this will be coming as our 4EH upon L. So this is our angle, and therefore we can summarize that for pure rolling condition we have that our omega is equal to Vx upon r, and horizontal distance between the bounds which is our L is our twice Vx square root of 2h upon g, and finally is our rebound angle and this rebound angle is with respect to horizontal, so we can say from horizontal which we just calculated is a tangent of theta is equal to 4EH upon L. So these were the two questions for our today's part, and specifically the second question is a little bit tricky, but it's based on the simple concept of our reversal in the direction of our velocity as well as our this projectile motion, because it will consisting of two parts, part A as well as part B. So this completes these two questions. Thank you.